All right, hey guys. I'm Mikhail, and this is my colleague and friend, Holland Wilkins. We're actually going to do something a little bit different today from other talks where we usually tell you about MLeap, how it's put together, what problems it solves. But today we're actually going to start with a short demo. So everybody go ahead and pull out your cell phones if you already haven't, and just navigate to this URL here. And we'll give everybody 10 seconds or something to go on there. But once you get there, and Holland will show you in a second, is essentially a very simple UI form. And it's connected to an MLeap model. It's just a very basic linear regression that's been trained on roughly 400,000 Airbnb listings from all over the world. And this is San Francisco, so how much you can rent out a spare bedroom or your whole house in the city is a very hot topic. So we just wanted to kind of hook it up to an MLeap model and see what that looks like. But nothing fancy. It's a form. It's hitting an API server. But what we want to do is actually, in real time in front of you here, in literally a few minutes, train a completely separate model. So what Holland's doing right now is he's choosing the Airbnb data set. He's choosing his dependent, independent variables, and we validated ahead of time. They're statistically significant and they'll work. He's choosing the random forest model. He's giving a little bit of metadata about it. And once he hits train and deploy, what it's actually doing, it's spinning up a Spark instance in AWS. It's constructing the whole transformation pipeline. It's training the random forest. It's serializing it into Bundle.ML, something we'll talk a little bit about later. And it's also deploying the model to a Combust API server. And the API servers will also go into at the end. So on that same page, if you hit the little refresh button, you'll see the numbers change. And what happened literally in these 45 seconds that I talked, we retrained the model in Spark, we serialized it, we deployed it to an API server, and this very simple form is now running on a random forest model. And this is really what our talk is about today. It's how do you take your Spark trained models and how do you deploy them outside of the Spark context? So what we want you to do is, do whatever you're doing today as far as using Spark for data processing for machine learning. But then when it comes to taking your ML pipeline models or your MLeap models, we want you to take a serious look at MLeap and how to deploy those out into production. So why are we doing this? We, not just us two, I think collectively, as a group, we've worked in teams of data scientists, researchers, engineers, product managers, and on teams where it's taken literally months, and I've heard stories of years where it's taken teams to deploy models out into production. This is what we want to solve for. We believe, and as we've demonstrated, the deployment of models can be very simple and very quickly, and that's what MLeap provides. And then one thing we talk about a lot, and this is really kind of our fundamental belief, is that the winning technology in the machine learning space will be the one that enables both data scientists and engineers to collaborate on the same platform. And there's a reason why we chose Spark and Hadoop to be that platform. So if you think about kind of the history of Hadoop, initially it gave us HDFS, which kind of solved the problem of having your data in disparate SQL systems, where if you're data scientist, you're pulling together data from all these SQL server, and then somebody on the engineering side has to replicate that. So Hadoop and HDFS solved that. Then Spark came along and provided a bunch of APIs and libraries for not only processing data, but also training models. So now that accomplishes the task of both data scientists and engineers are speaking the same language. So it's a lot easier for engineers to take what a data scientist has done in Spark and actually deploy it into a production environment. And then the third thing that we're providing is once your models are trained is how do you take those Spark trained models, how do you deploy them out anywhere on the JVM or on an embedded device or an API server like we showed you a second ago. And before we dive into talking about how MLeap actually functions, it's good to also talk about what other products exist out there, because they exist. They're very powerful solutions. Some of them are very popular solutions, but I just want to be very specific why MLeap is different and the problem that it's trying to solve. And you guys can read the slide, but really it's what's in column 1 is what we're trying to solve for. We want to essentially alleviate the work that engineers have to do to recode the models in a production environment, and we want to give them a solution so that they can instead refocus their time and efforts on more sophisticated problem solving and kind of working with data scientists on better machine learning solutions. And we're not the only ones thinking about this problem. Databricks, for example, has been working diligently to separate out the linear algebra library, so it's not attached to Spark. They actually had a release, I believe, a couple of days ago, or one of the Jira tickets got closed. That takes us a step further to that. So once that's done, it's going to be a huge add-on for MLeap, so that we don't have to maintain parity between some of the features between MLeap and Spark. Netflix did a blog post early February, I believe, about how their team is solving challenges between researchers and data scientists doing one thing, and then engineers having to recode features in a separate environment. And then there's also private organizations. So we talked to a company called DataJu who presented at Spark Summit East, and they've done something internally where they essentially try to disconnect the Spark models away from the Spark context and deploy it into production. So at this point, I'll hand it over to Holland to talk about how we've approached the problem and what our solution looks like.
Hey everyone, I just want to give you some of the technical details about how MLeap was actually implemented. And there are essentially 4 components to it. There's MLeap Core, the runtime, the Spark integration model, as well as the serialization module, which is the most recent one. And that we actually developed our own serialization format for that one called Bundle.ML. And I'll talk a little bit more about that in a second here. But the first module I want to talk about is MLeap Core. And MLeap Core has this linear algebra library that Mikhail was just talking about that Databricks, I think, is working with Netflix, and they got it separated from the main Spark project. But anyways, pretty much that provides our dense and sparse vectors as well as a basic linear algebra subprogram. Provides feature builders like a vector assembler, one-hot encoders, string indexers, hashing term frequency models, stuff like that. Linear regression models, random forest regression models, gradient boost decision trees, classifiers like random forest classifiers, support vector machines, logistic regressions, all that stuff. So really, MLeap Core is the building blocks for the rest of MLeap, and it's just the simplest versions of these models that you need in order to actually score data with them. MLeap Runtime is where all of the magic actually happens. This provides 2 data structures, the leap frame and the MLeap transformers. And the leap frame is pretty much a lightweight Spark data frame, very similar, except it only supports a few data types that you actually need to run your ML pipelines. It can be backed by a local array, or it can be backed by a distributed data set, so you're never going to lose the ability to execute an MLeap model against a distributed RDD or a Spark data frame. The other piece is the MLeap transformer. And that's pretty much exactly like a Spark transformer, except instead of operating on Spark data frames, it operates on MLeap leap frames. You see this sort of one-to-one correspondence between MLlib and MLeap, and that's very intentional. So if you see a string indexer model in MLlib, you're going to see a string indexer model inside of MLeap. If you see a linear regression model inside of MLlib, you're going to see a linear regression model inside of MLeap. And that's because we have to re-implement a lot of these things to operate on leap frames instead of data frames. The biggest thing about the runtime is that there are 0 dependencies on Spark. So you don't need a Spark context. You don't need any Spark jars. You don't need anything related to Spark in order to execute your Spark-trained ML pipelines. This is sort of a proof of concept feature pipeline that we built out. And it's very simple. Essentially, we're taking a set of continuous features, putting them together into a feature vector, scaling them using a standard scaler, taking categorical features, running string indexing and one-hot encoding on them. And then we're putting those together into a categorical feature vector, combining it with the scaled features that we trained before, and then finally what we have is a final feature vector that we send into a linear regression or a random forest model or whatever we want to train with it. And this is just sort of a nice, I kind of like this visualization. It shows what a leap frame looks like and how simple it is and what's sort of happening at each step in your transformation. And this is just sort of a zoomed in view of that string indexing followed by one hot encoder step. So leap frame is just a column with all of your rows as the data. In this case, the leap frame has one column called make and rows Honda, Ford, Nissan. And what you're doing when you send it through the string indexer is you're encoding Honda as a 0, Ford as a 1, Nissan as a 2. So literally all these transformers are doing is just taking your leap frame or data frame and pretty much just adding new columns to it. The next module that I want to talk about is MLeap serialization. And this is based off of a serialization format that we came up with specifically to solve the problem of how do we serialize both Spark models and MLeap models to the same format. And the solution to that was Bundle.ML. And what we really wanted to do is provide a very portable format. So we based everything on protobufs and JSON, which are highly portable across languages, across platforms. They're available pretty much anywhere you could imagine, all the way from C up to Java, Python, Ruby, all that. And we wanted, excuse me, we wanted JSON so that if you had a small model, we could encode it as a JSON, and then you could easily debug it and see what's going on. And then we also wanted to use protobufs so that if you have something like a random forest model with a lot of decision trees and a lot of nodes in it, that you could store it in a very compact format. One of the big differences between Bundle.ML serialization and out-of-the-box Spark serialization is that Bundle.ML does not depend on Parquet. And what that allows you to do is it allows you to take the serialization outside of the JVM, outside of Hadoop, and you can put it in literally any file system like data structure. So I like serializing them to zip files a lot because they're very portable. I can just send them in emails if I want to, or I can make a simple REST request to upload it to S3 or whatever I want to do with it. But you can just as easily store it on like HDFS or a local file system or whatever you want. This is just a few examples of what our serialization format looks like, and I'll actually go into a little bit more detail about it later, but I just wanted to show you guys this slide to show you how simple all of this stuff is. Just a few lines of JSON for string indexers, linear regression models, and actually at the bottom, just a few lines of code to actually implement a linear regression in MLeap core. This is the last module. This is an important one. This lets you actually take your Spark estimators and your Spark trained models and export them to MLeap or serialize them to Bundle.ML so that you can later load them up into MLeap. The other thing that it does is it allows you to execute an MLeap model against the Spark data frame. So you're not going to lose that ability to execute your models in a distributed context. And there's a little bit of complexity that goes on under the hood for these two operations, but they're just one line of code for developers. So it's very simple to perform these two operations. It does all the work for you. Benchmarks. So I wanted to simulate what it would be like if we were to actually run an API server with Spark data frames and a Spark ML pipeline versus a Leap frame and an MLeap pipeline. And so what I did is I took that feature pipeline that I just showed you, along with a random forest regression model, and I actually transformed 10,000 data frames as fast as I could. And I did that with Spark, and what I found is that it took about 23.4 milliseconds per transformation. When I did it with MLeap, it took about 11 microseconds per transformation. So there's a huge difference, about 2,200 times faster if you're using MLeap for this. And I was using local relations with Spark, so it was all locally backed data. The only problem is that Spark data frames are immutable data structures. So if you want to transform them, you have to create this thing called an execution plan. And then once you've created the execution plan, then you can actually transform your data. And that operation takes a long time. So that's why you see this huge speed difference between MLeap and Spark.
Yep. Actually, the first thing that we ever did was try to take like an API service and point it directly at Spark. So one thing I think you mentioned, these are all local data frames, so they're not distributed. If you try to run against a distributed data set, like your first request is going to take multiple seconds, and then your subsequent ones, depending on how you code it, you can probably get it down to like 200 milliseconds. But for us, really the goal is sub-millisecond response times because our audience is really that needs high-performance API servers, ad networks, pricing models, whatever you can think of. So the one thing that we kind of want to circle back to is our earlier demo, and actually talk a little bit about like what actually happens, on the back end. What does it actually look like? And to make things a little simpler, we put it into a Jupyter notebook. It's powered by Tori. It has a Spark instance running on the back end. So we'll just kind of walk step by step. So the first thing you see is we're loading data from a,
sorry, let me just.
Yeah, so we're loading data from our local file system, but you can just as easily load it from S3. The next step is we're imputing some metrics. We want to make sure that we don't have any nulls in the data set. Anyways, we can kind of skip over that. And to give you a sense for what the data looks like, the first thing as we see is like, okay, so most of the Airbnb listings are obviously New York, California, some cities in Europe. And then the next one is, and kind of question to the audience is, where do you think the most expensive Airbnb listings on average are? You guys can speak out. Okay, San Francisco.
Anybody else?
Moscow. Okay. Actually, I don't think Moscow was in this data set, although maybe. So let's take a look. Across the board, they're pretty much beach cities. So you got like Palm Beach, Malibu, Pacific Palisades, and Los Angeles. So if you have a beachfront property, you want to throw it up on Airbnb, you'll make a ton of money. So let's actually go through of how we construct that feature pipeline, that slide that Holland had of all the little boxes. So the first thing we do is we're going to define our categorical and continuous features. And then for the actual pipeline, we're actually going to build our transformation pipeline. So start out with continuous and categorical feature indexers and assemblers. We're going to do the one hot encoding. Again, this code is available for you. I'm not going to go through in detail. And at the end, we assemble our pipeline, and we're going to train two models. We're going to train, again, a linear regression and a random forest right here in front of you. He actually ran the whole notebook, so it's already ran. We're just kind of scrolling through. But the next thing we want to show is two things. One is that we get results back from a linear regression and random forest, and that they're different. But the one thing that we're looking for to be consistent is if we run the Spark predict method and also the MLeap predict method, that the results are the same, and they are. But what this should tell you is that we didn't screw up any implementation, and that when you're actually calling in real time, you're going to get back the same results as if you were running a data frame through your predict functionality. And that, again, the same for both linear regressions and random forests. The last thing we're going to do is we're going to serialize the models. And Holland's actually going to pull it up and show you what that serialization looks like. And as you remember, we have two options. We can do it as JSON and as protobuf, but if you want to show it to them.
Yeah, so this is all JSON right now, but like I was saying earlier, I want to
let's make it a little bigger.
Oh, okay. As I was saying earlier, I want to make random forest models encoded in protobufs. So anyways, this is what Bundle.ML looks like. It's a few files that have meta information related to some of our pipelines and also specific for Bundle.ML, like about the version and stuff like that. If we look at stage 0, which is our feature pipeline, you can see that we have feature assembler here encoded as JSON. We have a standard scaler here to scale those. We have our string indexers here. All is very simple JSON that you can just take a look at. We have our one-hot encoders here. And then finally, at the end, we have a feature assembler for the linear regression and a feature assembler for the random forest regression. And they're pretty much exactly the same, except for the linear regression features are all one-hot encoded, whereas the random forest features we just stop at string indexing for those. So this is the linear regression. This is the actual linear regression model with the coefficients and the intercept coded into it. As you can expect, it has an input features column and an output prediction column. And yeah, that's what Bundle.ML looks like. So the next thing that I want to do, actually, I'm going to start up some API servers using those models. So I'm going to start up a random forest model on port 8080. I'm going to start up a linear regression model that we just trained on port 8081. And then I'm going to go to this other notebook that we have here, which is actually going to make some RESTful API calls to those two servers that I just started up. And you can actually see the data that we're sending into it right here. We're sending in a schema with all of the fields defined, as well as the rows that we want transformed by our MLeap model. And we're posting it to localhost 8081, which is our linear regression model. So if we run that, happened very fast, but we just sent 50 requests to it with random data, and these are the predicted prices that we get back over here on the right. And we can do the same thing for our random forest model that we just fired up. We're sending the same exact requests to it, same exact data. Again, we're sending 50 requests out to it with random data, and now we're getting random forest results back. So this is really cool. Literally in about 2 or 3 minutes, we just went through a Jupyter notebook, trained a model, serialized it to Bundle.ML, and then loaded it up into 2 separate API server instances and started making requests against it. So that's exciting for me, for sure. Anyways, this is the future of MLeap. Said it a couple times now, we want to unify the linear algebra library with Spark, so it's less code for us to maintain. I think that's very important moving forward. I also want to get some of those core models, I want to unify those with Spark as well, so that you have string indexers and linear regressions and random forest models that are the same exact code that both MLeap and Spark are executing against. Within the next 6 months or so, I want to provide a Python interface, maybe an R interface. 6 months a little ambitious for that, maybe. I want to deploy easily to embedded systems outside of the JVM. So you shouldn't be limited just because you're training your model on the JVM. Doesn't mean you should be limited to executing your model on the JVM. You should be able to execute it anywhere that you want to. We also want full support for all the Spark transformers, and hopefully it's a lot sooner than a year, but that's worst case scenario.
Yep, and the last thing I want to touch on, or 2 last things. We mentioned something called Combust.ML. It's a few things. The first thing is it's the API servers. They're Scala-backed API servers that are built specifically for MLeap models. Again, I said we're looking for very high performance, so we are essentially going to be setting up or building API servers that are going to be extremely fast to score against. The second thing is it's really a platform for us to continue developing kind of the other functionality around deploying and kind of working in the machine learning space when it comes to kind of deploying your models outside of just the research environment. The first thing that we want to provide is really more essentially a public interface for you guys to go in to drop in a data set securely or point to like a secure S3 location and essentially have like a demo of what you saw earlier where you can like pick your data set, pick your dependent, independent variables, pick one of the I think like 15 models that we support, and essentially we want to be able to just like spin up an API server for you so you can actually go to your organization or whoever you're working with and be like, here's the model that I trained and here's something that you can actually like use today. To kind of get more people involved in understanding how MLeap and Combust works together. The other kind of big things that we're thinking about, again, it's a platform for us to develop things like like feedback loops, ensemble models, A/B testing. All that's going to be going into Combust.ML. And also the big thing that like I've been thinking about a lot, and I touched on earlier, is how do researchers and engineers work together to define features? So like the same code that a researcher writes to define a feature, it should be easily portable into the production environment. There should not be like duplication of code. You should be able to just ship that automatically. And the last thing is we just want to thank some people, especially those summits and places that have hosted us recently. So like Spark Saturday in DC, that was great. There's a Roaring Elephant podcast who are spreading the good word about MLeap in Europe. And also some folks that have helped us along the way, like Mishkin, who built this awesome UI for us, Priyana, who's in the audience, who's been working on making MLeap very performant, and Ram, who actually got us the first talk in Spark Summit East and kind of led us on this journey. And I guess the last thing I'll say is that we're definitely looking for people to contribute to MLeap. There's a lot of work to do, like you saw the timeline that Holland presented. But there's also a lot of integration pieces that we want to work on. We've had a few people approach us to essentially like contribute and develop, and that's worked out great. Holland's a great teacher. So if you want to contribute to this or test it out in your organization, please reach out to us. Here's our contact information, and yeah, we look forward to speaking to you after the talk, or feel free to ask questions here as well.
Thanks, everyone.
First question. Okay. My question is that how often do you actually upgrade the model and push the model into the production?
So here, this was just an example. You can do it as frequently as you want, really. There's no limitation. You saw how quick it was, right? By the time the model is actually trained and serialized, it's very small, so it's very easy to ship. So it's very easy. Like here, it was like we schedule it to update like every hour and a half or something. Yeah.
Enjoy your talk. Do you provide diagnostics for model training? For example, like in R, when you do a regression, you can output diagnostics, look at residuals.
Yeah, I think
and
that's
also cross-validation.
So all the training still happens in Spark. So anything that's available to you in Spark, you still have available to you, right? So I think Spark does offer you some data about your linear regressions and all that. So,
but we can definitely
still have
expose
access to
it. Like in the UI that you saw, like it's an easy thing to just like there was a talk earlier about like the R statistics, so we can definitely expose it in the UI as well. Yeah, but we're not writing our own code to do that. Yeah.
Now, question: the JSON format for trained machine learning models that you were showing, is that public and documented somewhere by itself? Have you considered that as a common format, like alternative PMML or something?
Absolutely, yeah. I'm trying to build up documentation for it, but there's a lot of work to be done. I have actually, if you go to Combust.ML and you go to the blog posts section, I have a short blog post about some of the basic ideas behind it. I have a sample implementation for both Spark and MLeap that you can take a look at for how it's implemented. And those files, if you train them, you can see it's pretty straightforward how they work, I think, with like a little bit of guidance from the blog post maybe. But yeah, like this would be a good alternative to PMML for transformer-based pipelines, I think.
In terms of your target market, what exactly do you mean by high performance? Do you mean high volume? Do you mean low latency? Do you mean both? Do you mean bounded latency? I'm just interested, what are you aiming for?
Both. We've talked to people like that have requirements for sub 5 millisecond response times for scoring individual records. So it definitely needs to be low latency. That's for like an ad platform that we talk to. But also they have extremely high volumes, so this thing needs to be able to scale as well, which is really easy because if you load the model onto one API server, you can load the same exact model onto 100 API servers serving the same exact model.
Okay, thanks. Anybody else? There you go.
Hi. I heard a lot about how this is sort of like independent of Spark in a way, that there's no dependencies on Spark, and how a lot of the functionality, I guess, in terms of data frames and things like that are also available in MLeap. But I guess I'm just trying to understand, like, to me, when I hear this, it seems like you're kind of reinventing the wheel. I wasn't really clear on what exactly. I mean, I know you're sort of productionizing code or whatever models, but like I wasn't really clear on, you know, if it's sort of, I guess, independent. Like, how am I sort of gaining by using MLeap instead of like Spark? I wasn't really clear on that.
So if you try to deploy a Spark ML pipeline to, say, Kafka or Storm or, I don't know, can you think of any other place? Like, if you try to deploy it outside of the JVM into Hadoop or Storm or Kafka or Mahout or somewhere like that that's doing stream processing, you would have to start up Spark contexts all over the place. It would be a very difficult process to do.
Yeah, the way I think about it also is like, I mean, Spark is definitely, you know, still part of your day-to-day workflow, right? Like building out the data pipelines, training the models. But once you actually need to take the model and deploy it outside of the Spark context, so essentially you don't want it running distributed, you don't want it making that execution plan every time you want to score like a single request, that's where MLeap supplements Spark. And like, I wouldn't message it that we are like independent. Like, it's just that we've created a way to make some things independent of Spark that enable, you know, the like essentially take your models and deploy them to high-performance API servers. But feel free to stop by afterwards. Like, happy to discuss this more.
Hi. This sort of reminds me of H2O. Is there similarity in what you're going after with H2O?
Definitely, yeah. H2O provides their own training algorithms and their own execution platform. I don't think it's transformer-based. So the MLeap is definitely very targeted towards Spark in the way that it has done everything. But
the one like kind of difference is like where H2O, I know they spend a lot of times like writing their own algorithms, and they have a great library for it. Our goal is not to rewrite, you know, how you train a random forest or a regression. Like, that stuff belongs in Spark. So that's what I meant by Spark really is the platform that we want to build on top of, because it already has a great community. For us, is just like, how do you take those models and how do you take them out of Spark? How do you take them out onto, you know, API servers or onto embedded devices or outside of the JVM? And that's really where we're focused on.
Okay, thank you very much. Give a big welcome and applause to them.